Hello, this is Math 25, section 3.1, rational functions. In this section, we're going to talk about domain and asymptotes about rational functions. So, since it says a rational function, so rational means a fractional. So, which means in the expression, you'll see the forms of fractions. So, because of that, we need to find the domain of the rational function. And also, there's a vertical asymptote, which makes the undefined case as a value of x. And then we can talk about the behavior at the vertical asymptotes, which is a horizontal or stunned asymptotes. We can talk about those asymptotes too. All right, so rational functions means over the last two chapters, the graph of linear, quadratic, and polynomial function has been studied. So one characteristic all three of these functions have in common is every linear, quadratic, polynomial function has a domain of all real numbers at the time, which means none of the number of the x value makes an undefined case. But the result was every line, parabola, and polynomial graph was one continuous line or curve that had arrows on both ends of showing the graph continues forever to the left and the right. But in this chapter, we'll study the function that does not necessarily have the domain as all real numbers. So the result is a graph that is often broken into the several pieces. So rational function is a function written as a ratio of the fraction, as I noticed that earlier, involving the two polynomials. So when you have actually the as a rational function, you get the two function. But each side of the function, g function and h functions are the polynomials. We already talked about polynomials, right, in chapter 2. So polynomial means the variable exponent is going to be the whole number. So recall that the linear quadratic functions are technically polynomial, even though the term polynomial is seldom used while discussing them. The following is a small collection of the example of the rational functions. So f of x, f function is a rational function because you have a polynomial, which is this degree of 1, and the 1 is a degree of 0, degree of 2, and degree of 0 for 4. Degree of 1 for g function, degree of 0, and degree of 1, and then degree of 0 plus 1. Degree of 2, degree of 0 for negative 1, and degree of 1, and then negative 3 is a degree of 0. X is a degree of 1 and x squared is a degree of 2 and then 3, which means all the degree of the variable as a term or the constant term is a degree of whole number. So domain of the rational function. So from the arithmetic, we must recall that division by 0 is always undefined. So for rational functions, this equates to the requirement that the denominator of the rational function never allowed to be a 0. So this is the basic for the finding the domain of the rational function. So we have to set the domain is not equal to 0. So with any rational function, we must make sure that the denominator is never equal to 0. So what is the domain in here? So which means all real number, of course, but except that there's number that we can use. So in order to get a domain, you might want to set the denominator set equal to 0 and then solve for x. And this equation actually you can add for both sides in order to get x squared equal to 4. And then square to both sides plus minus sign because the root is always 2 of the square. And then plus minus 2. Which means we cannot have a 0 in the denominator. So x cannot be the plus minus 2. Which means the domain is, for this case is, all real numbers except x equal to plus minus 2. So all real numbers fine except the 2 and negative 2 because 2 and negative 2 will become the undefined case. What is the domain for the g function this time? Which is, we need to set 2x plus 1 equal to 0 and then solve for x. Which means 2x equal to negative 1 divided by 2. So this one. So, which means all real number, I'm talking about domain, all real numbers except x equal to negative 1/2. What is the domain for the q functions? Yeah, same thing. We have to say x minus 3 equal to 0, which is not equal to 0 actually, right? So at 3, x equal to, not equal to 3. So all real numbers except x equal to negative 3. So all terms are fine except the negative 3 because negative 3 makes an undefined case. Alright, for the number 4, yeah, x squared plus 3 equal to 0, but not equal to 0, right? So subtract 3 both sides, x squared equal to negative 3. So for x equal to plus minus, but there's a negative sign in the square root, which means you're getting an I, but 3 is not a perfect square, it's this. Which means this is not real. So which means it's okay. X is not going to be the real number anyway. So in this case, it's going to be all real number. Because the number that unavailable is going to be the not a real number case. So this case is all real numbers. So whatever number you have and plug into the X place, it makes all the defined case. Excuse me. The vertical asymptotes. The vertical asymptote, to find it is, now we're gonna say, not the domain, sorry, denominator. We need to say denominator equal to 0. Okay, so in denominator not equal to 0, then we're gonna find the domain. And then the vertical asymptote, we just need to set the denominator equal to 0. Okay, so effect of the domain restriction of the rational function will be break in the graph. A domain restriction of the one value will result in two unconnected pieces to the graph. Domain restriction of the two value will result in three unconnected pieces to the graph. This pattern will continue indefinitely where for any number of the domain restrictions, there will be the one more than that number of the unconnected pieces to the graph. So at this breaks, the most typical behavior will be a graph getting closer to vertical line on each side, extending the upward, downward, but never touch the vertical line. The vertical line is called the vertical asymptotes. So example 1 from the example, we already found the domain, isn't it? So as a domain, x cannot be plus minus 2, right? But as a vertical asymptote, we need to set denominator, which is x squared minus 4 equal to 0, which is so for x. So x equal to 4, square root of both sides, always plus minus. So x equal to, this is actually the vertical asymptote. The difference between the vertical asymptote and domain is, domain cannot be that number because it makes undefined. But we are looking for the vertical asymptote, so it's okay to put the x equal to 2 and x equals minus 2. So let's say 1 is a positive 2 here, 1 is a negative 2 here. Asymptotes, we always put the dashed lines. So this is it, which means when you're graphing the rational function, we won't touch at the 2 and negative 2 as x. Example 2. Now we have a vertical asymptote, which is, set 2x plus 1 equal to 0, and so for x. So 2x equal to negative 1 divided by 2. This is 1. So this one has only one vertical asymptote, which is a negative 1/2 in here, and these are the vertical asymptotes. Okay, let's look at the example 3. Where are the vertical asymptotes for that? So cube function denominator is x minus 3 equal to 0, plus 3 both sides, x equal to 3. So this is the vertical asymptote, which means x equal to 3 is about here. So this is the vertical asymptote. Example 4. Where the vertical asymptote for the r of x, which is x squared plus 3 equal to 0. So for x squared equal to negative 3, x equal to plus minus, go to both sides, right? And then 3, and there comes I, which is not a real number, which means you can find the I number on the x-axis. So this time is no vertical asymptote this time. Alright, so after this, for example, the domain restriction and the location of the vertical asymptotes for the rational function may seem to always do the same. There is one case where this will not be true. Consider the following example. So consider f of x is 2x plus 6 over x squared minus 9, which by factoring can be written as this. And then domain of the f of x is going to be, x can be 3 or negative 3, which is that's the domain is all real number except this. But notice that there's a cancellation this time, which means x plus 3 cancels out. So you can reduce this expression as 2 over x minus 3. So for the vertical asymptote, we're not counting the one, the linear factor has been canceled. We only the one that is not canceled, okay? So in this time, we just need to set x minus 3 equal to 0 for the vertical asymptote. And then add 3 both sides. The only the x equal to 3 will be the vertical asymptote. So x plus 3 will be makes us something else. Okay? Alright, next pages. The factor x plus 3 in denominator of the original version of the function restrict the negative 3 from the domain, but because of the factor x plus 3, it will be divided out. The function will not have a vertical asymptote of the x minus 3. Instead of the vertical asymptote, the graph of the f of x will have a hole this time at the x equal to negative 3. So if the function has a factorable numerator and denominator, it will be a good practice to write the function in factor form to determine if the function has a vertical asymptote or holes. Okay, it's from the denominator, the graph at the restrict domain values. Behavior at the vertical asymptotes. After finding a vertical asymptote and knowing that a rational graph will never cross the vertical asymptote because they occur at the domain restriction, the next topic to discuss is the behavior of every rational graph as it approaches the vertical asymptote. Consider the following function. So we have function like this, which means domain cannot be 1, right? Because when you set x minus 1 equal to 0, yeah, you see that the x cannot be the 1, right? So there's a 1 in here, which means this is the vertical asymptotes. And then determine what graph will do it approach the vertical asymptote x equal to 1. The following two tables that describe the point of the function as approach to 1. So we are using in this case, we are using 0 right here, negative 1.5, and then getting close to 1, right? Negative 0.19, 0.99, and then as you notice, the value of the y is gonna be the very, very big, isn't it? So which means from here to over here, right? So which means and the negative 3, and then it's getting bigger and bigger, right? So you get this kind of graph. It's going down this way. And then like what about 2 here? So about 2 about the 2 is going to be 3, and then 5 is about 6. Well, 1.1 is here is 30. Hold on a second. Yeah, I don't think this is true. 2, 5, 1.1, and 1.01. Yeah. So I think the graph should be this way. So as if you plug it in 5 in here, hold on a second. I don't think this is true. I think this is 1, right? So if you plug it in, 3 over 5 minus 1 is actually 3/4. I don't know how we get the 6, which is down here. So it can't be this one, okay? So let me erase this one. Sorry about that. Yeah, so this kind of graph we'll get. So first table has x value that has approaching 1 from the left side. The second has the x value that is approaching to 1 from the right. So considering the portion of the graph containing these points for the f of x equal to 3 over x minus 1, we see that the graph will be the pointed nearly straight down on the left side of the vertical asymptote and nearly the straight up to the right side. So which means from the 1, right? And then your graph going to be this way and then this way. It depends on where you're approaching it. Okay? So when x goes to infinity, which means going to the 0, f of x goes to 0. But x goes to 1, it's going to be the positive infinity, or other side is going to be negative infinity. So for the either side of the vertical asymptote, the graph of the rational function approaches to the positive infinity because this is a positive infinity approaching, and then this is a negative infinity approaching to the 1. Alright, so in other words, as the curve gets closer to the vertical asymptote from the either side, the graph will be the pointed nearly straight up or the straight down. So, and behavior of the rational functions, okay. So we have two polynomial. I put it here. So this is a leading coefficient and this is a leading term as a degree. And denominator is bk is a leading coefficient and then k is a degree of the denominator. So the final topic of the discussion regarding the rational function in this section is end behavior of the rational graph. Record that for the polynomial function, the end, the behavior controlled by the degree of the leading coefficient. This is what I put it. It's a numerator and this is the denominator. Since the rational functions are the ratio of the two polynomial functions, the end behavior of the rational function is controlled by the degrees and the leading coefficient both of the numerator and denominator. These three cases we'll study will have the end behavior where the graph will approach the line. Two cases, the end behavior will be a graph of the approaches a horizontal line. We call the horizontal asymptotes. For the third case, end behavior will be graph approaching the line positive and negative slopes called the slant asymptote. So case 1, we are getting the horizontal asymptote. So if the degree of the numerator is less than degree of the denominator, so n less than k. The rational function will have the end behavior approaching the horizontal asymptote, which is y equal to 0. So what is the end behavior? So for this function, so degree of the numerator is 1 because degree of 1, and the degree of denominator is 2 is the 2, okay? So so when I compare, 1 is less than 2, so which means we'll get the y equal to 0 horizontal asymptote. So which means n behave the function, so when x is approached to the positive infinity, and then the f of x goes to 0, and then negative infinity also goes to 0 too. So infinity to the negative infinity. Okay, case 2. The degree of numerator and denominator are the same, which is n equal to k. The rational function will have the n behavior approaching the horizontal asymptote, which is y equal to leading coefficient ratio, where a and b are the leading coefficient of the numerator and denominator respectively. So example 2 again, what is n behavior for the g of x? So degree of 1 and degree of 1. So this one gets the same degree here, which is the leading coefficient 3 and 2 will make the horizontal asymptotes. So horizontal asymptote is 1.5, so it's about here. Okay, so and then graph goes in, and then the end behavior, it doesn't matter which it goes to, it approaches the 3 over 2. Case 3, if the degree of the numerator is greater than the degree of the denominator, which is n greater than k, the rational function will end behavior approaching the slant asymptotes. So which is slant asymptote becomes the line that y equal to mx plus b. But if the degree of the numerator is 1 greater than the degree of the denominator, especially we get the slant asymptotes. Otherwise, there's no horizontal or slant asymptote. So what is the end behavior? So since the degree of 2 and degree of 1, so 2 is greater than 1, so we get the slant asymptote. So in order to get a slant asymptote, we need to divide. Long division. So x squared minus plus 0x minus 1 divided by x minus 3. So x squared divided by x is x, which is x squared multiplied minus 3x. Subtract. We got 3x drop negative 1. And then 3x divided by x is a plus 3, which is 3x minus 9. And then subtract. We got a, but we only take the quotient. So this is it. So this is slant asymptote. So in order to get the slant asymptote, 1, 2, 3, and then slope is going 1 and 1, right? If you put it right there, right? Yeah, so you will get the graph of this. This is a line, which is what? It has to be the slant asymptote. So, well, here. So this is slant asymptote, which is a dashed line. Okay. All right, so that's all for the this sections. So thank you for listening.